In the first video, we talked about the structure of an atom. We said that there's three parts that make up an atom. You got the protons, the neutrons, and the electrons. The electrons are negatively charged and they move around the outside, and they can be traded from atom to atom, and they get traded in a direction like hot potato, going from one to the next to the next to the next. Then that's an electric current, and that's where electricity comes from. We talked about induction, and anything that can spin a coil of wires inside of a magnetic field can induce an electric current in those wires, and that's basically how we get electricity for all of our forms of power, solar being the main exception to that. So, for example, in a coal-fired power plant, you burn the coal to generate a whole bunch of heat. That heat boils some water. That boiled water turns to steam and it wants to expand. You can capture energy from that expansion, force it to drive the spinning of these turbines, and as the turbines spin, they spin a coil of wires inside a magnetic field. There's these big magnets inside there, and that generates the electric current, and that's how you can burn coal to get electricity. And same goes for all of the other forms of fossil fuels getting burned. That's how you can go from a combustion reaction to getting electric current. Now, the exact same thing is going to be how nuclear reactors work. We get electricity from a nuclear reactor by heating water. We're interested in the heat, and that heat is going to heat up some water. That's going to generate steam. That steam is going to turn a turbine. That turbine will give us the electric current. But in order to understand how a nuclear reaction works, we need to know about the other parts of an atom as well, because this, after all, is atomic power, from an atom power. So we've talked about the electrons. They're the parts around the outside that can move around more freely. But the dense center of the atom, where most of the mass of the atom actually is, it's where all the weight comes from, is called the nucleus. That's the center of the atom, is the nucleus. And it contains two kinds of particles, protons and neutrons. Protons are positively charged. Neutrons have no charge. And they're mostly there to kind of hold the protons together, but also keep them a little bit spaced out because positive charges repel each other. So it's good to have a few spacers in there so they don't just kind of blow apart. Really helps stabilize the whole thing. Now, when something is radioactive, it's in fact unstable. It has the wrong number of neutrons in there. It might have too few neutrons or too many neutrons, but you can see the role of the neutrons as stabilizers, because if you have the wrong number, it becomes radioactive. And what a radioactive element is one that where the nucleus is breaking down. Pieces of it are flying off. So little clusters of protons and neutrons are shooting out every which way. And during that reaction, which we call nuclear fission, nuclear as in the nucleus of the atom. So anytime we're talking about nuclear physics, we're talking about the very center of the atom, physics associated with the center of the atom. Every time a fission reaction like that occurs, where a piece of the nucleus breaks apart, it generates just gobs and gobs and gobs of heat. Lots of energy is released in that process. Because what happens is a little bit of the mass of the atom just gets converted to pure energy. And that sounds a little bit weird, right? It's physical matter being turned into pure energy, but as it turns out, energy and matter are related to each other. They're different forms of the same material. And that's what Einstein's famous equation E equals mc squared is talking about. The amount of energy that you would get from some block of matter, if it was completely transformed from its mass into energy through this kind of a process, is equal to how much it weighs, its mass. Weight and mass are slightly different, but we'll just say how much it weighs, times the speed of light, which is a very large number, squared, right? So you get lots and lots of energy out of this reaction. Fortunately for us, only a little bit of the nucleus actually gets converted. Only a little bit of the material there gets converted to pure energy, so it's much more manageable than if the entire block of uranium that we were working with just suddenly turned into energy. That would just be too much to work with. So, we have the protons and the neutrons in the center. Now, the cool thing is we can actually induce a fission reaction by shooting a particle at the nucleus and hitting it. Right? So it's kind of like in pool, right, where you get the whole stack of balls right at the beginning, right? You have the rack of balls, that's what they're called, in the center, that triangle, and then you shoot the cue ball at it, and they all kind of scatter all over the place. That's kind of how fission works, right? The nucleus is the cluster of particles, and then you have one particle that you're going to fire at it, and it breaks everything else apart. Now, we couldn't use a proton for that because a proton is positively charged and the nucleus has an overall positive charge because it's got protons, which are positive, and neutrons, which have no charge. So if you try to throw a positive thing at a positive thing, it's just going to veer off in the wrong direction and it's going to never hit it. So what we have to use are neutrons. We get neutrons and we fire them at the material that we want to induce the fission effect in, and that periodically a neutron will hit the nucleus and it'll rupture it, it'll cause it to become unstable, and that will cause it to break apart and release all of that energy. Now here's the cool thing about nuclear fission reactions. In the process of breaking apart, it makes more free neutrons. It's going to shoot out more neutrons in random directions. If you have a block of material, each atom that breaks apart in that way, that undergoes fission, it's going to shoot out neutrons, and those neutrons can potentially hit its neighbors, all the atoms around it, and then induce them into a fission reaction. And then all of the neighbors can induce their own fission reaction. And because every time a neutron hits a nucleus, it induces a brand new fission reaction with gobs of energy being released, it never really slows down. It just keeps going and going and going and going. And this is what we call a chain reaction, a sustained chain reaction. So once we get the ball rolling, the reaction can actually just run away with itself. So one of the main things we have to worry about with a nuclear reactor is controlling the fission reaction. So, nuclear fission is the process of splitting atoms, specifically splitting their nuclei, the nucleus of the atom. This provides a lot of heat. The reactor boils water to produce steam, and then that steam spins a turbine. The fuel for this reaction is uranium. It's a inherently radioactive material. Actually, fun periodic table fact, every element that is heavier than lead is at least a little bit radioactive. There are radioactive isotopes of the elements that are lighter than lead as well, but there are no stable isotopes heavier than lead. So why does uranium have to be the fuel then? It's just really, really good for sustained chain reactions. It produces the right number of neutrons per fission burst to get this nice chain reaction going. So, these uranium chunks are refined into these nice cylindrical little pellets. See them there? And then those pellets are arranged into these fuel rods. And then the fuel rods are placed into a fuel assembly in this nice stack right here. And then those fuel rod assemblies are placed into the reactor chamber. There may be as many as 51,000 fuel rods in a power plant. So this GIF should give you an idea of how nuclear fission works. You can see here that we start out with an atom of uranium, and you can see it's a much larger, more complicated nucleus than the helium atom that we started out looking at. And an accelerated neutron is fired at it, bam, hits it, makes it unstable, and it breaks apart into two smaller nuclei. Now, the number of protons that are in a nucleus determines what kind of chemical element that it is. So if you break it in half a little bit unevenly, there's going to be a different number of protons in one chunk than there is the other. So that's why it splits from uranium into krypton and barium. Uranium has 92 protons, but those 92 protons break apart into two chunks. One chunk has 36 protons, that's krypton. The other chunk has 56 protons, that's barium. The other thing that's important here is that if you add up the mass of barium and krypton, and that's the number at the top here, 142 for barium and 91 for krypton, you're going to come to, that would be 233. The mass of uranium is 238. So we went from 238 to 233 between these two. Where'd the rest of the mass go? Well, you can see some of it is in these neutrons, right? As it broke apart, some of these neutrons went out there. So we got 3 neutrons out there. That adds another 3 mass to this. So we went from 238 to 236 now. Where'd the rest of that mass go? That's what got converted to energy. That's the fission reaction, converting a little bit of that mass over to energy there. So lots of energy is released, but also some free neutrons fire out. And those neutrons, next little GIF here, can ram in to adjacent uranium nuclei, and then every time you get another fission reaction, another 3 neutrons are released, firing towards all the adjacent atoms, and you get more and more radioactivity. You get more and more fission going on, and every single one of them is converting more of the mass into energy and creating more and more heat as a result. So while the goal is the same, which is to heat up water, the way that we're going about heating up that water is fundamentally different. Coal and oil and natural gas is just combustion reaction. It's simple chemistry. This is nuclear physics. We are literally splitting atoms to release some of the energy which is held inside of them. Now take a look at what this slide notes. Several neutrons are produced from each fission event. This could lead to a runaway reaction, because if every fission reaction leads to 3 more and 3 more and 3 more and 3 more and 3 more, then you're just going to get an exponentially increasingly large fission reaction, which that's how a nuclear bomb works, is you just have a runaway fission reaction. So in a commercial reactor, we have to control that reaction. We do this with cadmium rods. Cadmium is another chemical element, and they are able to absorb excess neutrons without undergoing fission. So engineers will eke in these cadmium rods. They'll kind of interlace them with the uranium rods in order to absorb some of the excess neutrons, slow down the fission reaction because there's fewer and fewer free neutrons hitting the uranium targets. And therefore, they will slow down the overall reaction, reduce the amount of heat generated. So by lacing in these cadmium control rods with the uranium fuel rods, we can speed up the reaction and slow down the reaction. As per usual, I got some vocabulary words from your learning objectives for you guys to write down, memorize. Reprocessing. Reprocessing is the process of getting some material out of the spent fuel rods. So eventually you use these fuel rods long enough, they've done as much fission as they can, they kind of slow down, they're not as useful anymore, but that doesn't mean that all of the uranium, the usable uranium inside them, is gone. And also in the process of using them as nuclear fuel rods, they will actually create another kind of material called plutonium. And plutonium is also extremely useful for certain applications, nuclear weapons in particular. If you've ever heard political discussions about whether or not a country should be allowed to develop a nuclear program to create nuclear power generators, and you ever wondered, like, why would it be a problem for them to create a nuclear power plant? They're not trying to make a bomb. You can't create a conventional nuclear fission power plant without creating plutonium as a byproduct, which is required for nuclear weapons. So that's part of the reason why that's a controversy. The next vocabulary term here is moderator. A moderator is a material which slows down the neutrons after they are released from the fission reaction. And note here it says causes more fission. This can be a hard concept to wrap your head around sometimes, because you would think the faster the neutrons are, the more vigorous the reaction would be, right? That if they're hitting the nuclei harder, that's going to be an even more impressive, like it's going to shatter it even more, that'll release more energy, more neutrons, and you'll get even more fission reactions. But it turns out that neutrons that are moving too fast don't have the right capture velocity. They are just not going to be as good at creating a sustained chain reaction as neutrons that are moving at just the right speed. So this moderator is used to make sure that they're going at just the perfect speed for a sustained reaction. If I can call you back to the shooting pool analogy, if you've ever seen one of those really nice trick shots where the person breaks the cluster of pool balls and they sink a whole bunch of them into the pockets at once, right? They didn't shoot as hard as they possibly could. That would potentially cause the cue ball to skip right off the table and miss the cluster entirely. They hit it just perfectly. They hit it with exactly the right force, exactly the right position in order to get that reaction to go. And so this is kind of the point of the moderator as well. And it turns out that water is a really good moderator. So we already need to heat up water for this reactor to work in order to generate steam. So we just bathe these fuel rods in water. It acts as both a moderator and it helps to capture all the heat that is created by this reaction at the same time. So it's really efficient. Sometimes graphite can also be used as a moderator. Finally, control rods. These are the cadmium rods, which can be slid in between the uranium fuel rods and slows down the nuclear reaction by capturing excess neutrons, preventing extra fission events from occurring. And you can actually see a kind of diagram up above on the left. We have the cadmium control rods, the green ones, in place, and the uranium fuel rods, they're only able to exchange a few neutrons between them because the control rods are in place, so there's some heat generated, not too much. But then we remove the control rods and more neutrons can bounce in between these fuel rods, so there's more and more and more heat generated as a result. If we were to put them in a little bit more, you would get a warmer reaction, but not too warm, right? The more you slide them in, the lower the reaction is going to be. The more you pull them out, the faster the reaction is going to be. Now, the water that is heated up by the fuel rods, the water that is directly in contact with the fuel rods, that is kept in a loop of pipes and is continuously cycled around. It's kind of pumped around in a circle. It is connected to another set of pipes with water in it that exchange heat between them. And it is that water in the second group of pipes that gets turned into steam and is allowed to turn the turbine. So the radioactive water doesn't actually come into contact with the turbine. It's a separate set of water. The only thing that is exchanged between them is the heat, not the radioactivity. So you have the second set of water that gets heated up by the first, turns to steam, and then turns the turbine. Then the steam is deposited into this condenser chamber here, and that's the next vocabulary word, is the condenser. Once the steam enters the condenser, there's a third loop of water, which is usually cooling water from a river. Typically, nuclear power plants are built along water sources, lakes or rivers, that kind of thing. So you bring in cold water from the river, pump it into this condenser in a closed loop again, and because you are bringing this constant flood of new cold water in, it's getting heated up by the steam, but then it's allowed to leave and return to the lake. So it's coming in cold, it's leaving a little bit warmer, but it's a continuous flow. And that's going to cool down the steam, return it to its liquid form, which will then allow it to drain down into the pipes. And then it can be pumped back to get more heat from the reactor chamber, and then get turned into steam again, flow to the turbines, and that's what powers that loop over there. So the condenser has this role of recovering the steam that passes through the turbines, and it maintains this vacuum to optimize efficiency, right? The whole thing is operating on this hot-cold system. And I think this will make more sense when I show you the full diagram of a nuclear power plant. But the condenser is here to cool down the steam from the turbines. Then you have these cooling towers. So the water that comes in from the river or lake and then exits a lot hotter than it came in, right? And you don't want to dump hot water directly into a river or lake because fish and other aquatic organisms are very sensitive to fluctuations in temperature. So you want to cool off the water first. And what you do is you let the water spread into these cooling towers. They fill kind of the bottom of these cooling towers, and they're allowed to cool off. And in that process, they too generate a whole bunch of steam, which pumps out of these cooling towers in the form, it looks like giant clouds coming out of these things. If you've ever seen driven by like Limerick nuclear power around here or other nuclear power plants, this is kind of what they're almost most famous for. It's how you can spot a nuclear power plant a mile away from these giant cooling towers. This one's obviously from The Simpsons, right? It's how you can tell it's a nuclear power plant from these giant cooling towers here. Very different from the smokestacks that you see on coal-fired power plants. And they look like cloud generators because of all the steam coming out. Now that water, it's just water vapor. It's just steam coming out of there. There's no other kinds of pollutants or smog or anything like that in it. And it's the cooling water that came from some sort of local source and is just being cooled off so it can be sent back to the environment. It's separated from the radioactive water by 2 loops. So it's in no way, shape, or form in contact with the radiation itself. It's just non-radioactive water that's been heated up and needs to be cooled down before. On this next slide, we bring everything together. The red chamber is the reaction core. You can see that it's filled with water, which is acting as a moderator to slow down the neutrons, which actually has the effect of increasing the number of fission reactions. And also it's surrounded by water in order to capture all of the heat from the fission reactions, right? Water is really good at storing massive amounts of heat. So you have your uranium fuel rods as well as your cadmium control rods in this diagram here. And you'll notice that the reaction chamber is contained inside this metal pot here, right? This has to be a very, very sturdy, reinforced vessel because this is going to be under pressure. And that is where a lot of any kind of accident from a nuclear power plant generally comes from, is from the amount of pressure that this reaction core needs to be under, because this water is heated way, way, way past the boiling point. This is incredibly hot water that is contained inside this vessel right here. And then the building itself, right, there's going to be a concrete reinforced building right here to make sure that no little bit of radiation can possibly seep out. So the water, the superheated water, goes through this primary loop and is cycled around, and you can see it moves into this area where it comes into contact with the secondary loop of water. So this is a completely separate secondary set of water. The only thing being exchanged between these primary and secondary loops is the heat inside. So this cools down the water from the reaction chamber and it heats up the water in the secondary loop, turning it to steam. That steam goes through this pipe and then it spins the turbine. The turbine, that's those magnets and coils of wire, and if they spin, they generate electric current, right? So anything that can spin this turbine will generate electricity. And the amount of steam that's being produced will spin these turbines really, really fast, so you get a lot of electricity out of this. So once the steam spins them, it then proceeds into this chamber here, where it comes into contact with the cooling loop. This is the water from a local lake or river coming in. Now, because this cooling loop is down here below the turbine, right, the steam is precipitating out down here. It's being turned back to liquid, so it's like rain. It's falling down here. And that means that there is a directional flow, right? It falls down this way and then it turns to steam over here, rising back up. So this forces the water to go in this clockwise flow around this loop. And it is a vacuum, right? It's a completely sealed loop here. So nothing is entering or leaving this. So that it's really important that that is sealed and that this cooling loop is here in order to help sustain that motion that's going on. The cooling water enters, gains heat from the condenser, and then is taken back to the cooling tower, where that's where you see these plumes of steam rising from nuclear power plants as the cooling water cools off and then is returned to lakes or rivers or wherever it came from. So, as you can see, the radioactive water that's in the containment building never comes into contact. It never physically comes into contact with the water in the secondary loop. Only heat gets exchanged. But it definitely never comes into contact with the water that's going into the cooling tower. So you don't need to worry about radiation coming out that way. I'm just going to go through this one more time, but I'll read all of the little indicators here. So number 1, fission occurs in the reaction core where fuel rods are submerged in water. The water slows neutrons in order to initiate chain reactions in uranium-235. In the fuel rods, while control rods absorb excess neutrons to regulate that reaction. Water heated by fission circulates through the primary loop, which is pressurized to prevent boiling. Water heated by fission in the primary loop boils water in the secondary loop, creating steam. Oh, I should probably explain this. When in number 2, where it says that it's pressurized to prevent boiling in the primary loop, the more pressure you apply to a heated system, the more it's going to tend to stay as a liquid. You can kind of fight against its phase transition by applying more pressure. So the fact that it's under pressure means it's not going to escape into the steam, into the gas phase. Number 4, the steam drives turbines which generate electricity. Number 5, cold water from the cooling tower circulates within the cooling loop, condensing the steam in the secondary loop and converting it to liquid water, which then returns to be boiled by the heated, pressurized water of the primary loop. So there's 3 loops of water here. You have the primary loop, secondary loop, and the cooling loop. Primary loop is getting heated by the reaction. The secondary loop is the one that's turning into steam and actually turns the turbine. And the cooling loop is just pulling heat from the secondary loop and then taking that to the cooling towers and to turn into steam. So what are the pros and cons of nuclear power? Now that we know how nuclear power works, what are its pros and cons? Well, one pro is that it actually has very little environmental impact. Apart from the carbon emissions associated with building the power plant itself, because obviously any construction project requires construction equipment that need to be fueled, and it requires some carbon emissions in the production of materials for it. So apart from those carbon emissions that are just unavoidable with any construction project, the creation of electricity just from the fission reaction doesn't create any greenhouse gases. It doesn't emit any pollutants into the atmosphere. It just creates steam. Energy yields are low to medium for the amount of time investment to get the energy to what you actually get back, but newer technologies are actually improving this, so in the future we might get that to a much higher net energy yield. Also, although it has a lower or medium net energy yield, the amount of uranium or thorium or other types of radioactive materials that we have available on Earth to use for this process is ample. It is a non-renewable resource. We're not getting any more of them once they're used up, but you need very, very little overall to actually create a fission reaction to get a lot of energy out. That's the amazing thing about nuclear physics, is how much energy you can get from a very tiny amount of material. So this could be an energy solution that lasts us a pretty long time into the future. However, it does generate radioactive wastes, and we do not have a good solution for those radioactive wastes right now. And the radioactive wastes stay radioactive for a very long time. And you can see how long they last by taking a look at what's called their half-life. The half-life is the amount of time that it takes for 50% of a material to break down through radioactivity naturally. So uranium-235 itself has a half-life of 700 million years, which is to say if I had 16 pounds of uranium-235, that after 700 million years, it would be 8 pounds of uranium-235. The rest of it would have decayed through radiation, through radioactivity. After another 700 million years, it would be 4 pounds of uranium-235. After another 700 million years, it would be 2 pounds of uranium-235. Now, the nuclear waste that are generated by nuclear power plants, we've already taken that material and accelerated the rate of fission pretty substantially. So the waste is not going to last nearly as long as just like a block of U-235 would, but it can still have half-lives of up to 30,000 years. 30,000 years is longer than the entirety of human recorded history. Way longer, in fact, and that's the amount of time it takes for the material to reach half of its radioactivity. It would take another 30,000 years for it to reach a quarter, and another 30,000 years for it to reach an eighth. So the nuclear waste generated by nuclear power plants is not something that we can just deal with in a haphazard or in a temporary fix kind of way. It's going to remain dangerous material for all intents and purposes forever, from a human perspective, for eternity into the future. So how do you dispose of material that is going to be dangerous over this long of a time period? We're talking all of our records could be wiped out, right? A completely different human civilization might discover it in some point in the future. How do you dispose of something securely that is going to be dangerous that long into the future? And I'm actually asking because, frankly, we don't have any really good solutions for this yet. I can tell you what we currently do. After about 3 to 4 years, the radioactive uranium fuel rods, in any of those fuel rods we talked about, become spent and they have to be stored. And they get stored in these structures here. They kind of look like big old water heaters, like you might find in your basement. They're significantly larger than that. And they're called dry casks. To give you an idea of how dangerous this material is, 10 years after a single rod is removed, the radiation is still lethal. You would die if you were exposed to it for 3 minutes from a meter away. So this is extremely dangerous material. Storage in dry casks or ponds, and this is not like a natural ecosystem pond. This is like a concrete man-made structure, which we refer to as a pond. It may be sufficient for about 100 years, but not for 1,000. They're simply not made for long-term storage. They were always meant to be a staging area to be shipped to a longer-term storage facility. These dry casks and concrete ponds, they are on site at the nuclear power plant, so they're just building up waste, more and more waste as they go. Note here, it says, after 3 to 4 years, the radioactive uranium fuel rods become spent and must be stored. And what did we learn on the first slide of this video? There could be about 51,000 fuel rods in a single nuclear power plant facility. So think about that. Every 3 to 4 years, each one of those rods needs to be switched out, and there's 51,000 on site. That is a lot of nuclear waste that needs to be stored. Now, if you think that's bad, wait till I tell you that the entire nuclear power plant can only be used for about 50 years, and then it needs to be decommissioned, decontaminated, and all the radioactive parts also need to be moved to some sort of secured storage facility. So globally, there's about 430 commercial nuclear power reactors. And of them, about 285 need to be decommissioned. And this is from your textbook. It said they will be decommissioned by 2025. I mean, I'm not psychic, but definitely not all of them are going to be decommissioned. Since 2013, about 8 have been decommissioned in the US, and there's maybe another 6 that'll be decommissioned by 2025. But we are probably going to try to use them as long as we possibly can, and it seems safe, because there's a lot of pushback against building nuclear power plants, but they do generate quite a bit of electricity in the areas where they are already established. So I would expect that a lot of governments and private companies that run these power plants are going to fight to keep them open for as long as they possibly can. However, when they are decommissioned, because they will eventually be decommissioned, there's two possible solutions here. You could go the Chernobyl route, which is to encase the entire plant in a reinforced steel tomb. They just basically took a giant steel dome and they put it right over Chernobyl. That encased all of the radiation inside. That was sort of an unusual situation. The other option is to dismantle it and then take all the radioactive parts, the parts associated with the radiation chamber and the primary loop, and store that in a permanent repository. So, what kind of permanent repositories are available? Well, there is a facility called Yucca Mountain, which has been set aside as a location to store the nation's nuclear waste underground for many years. It's been established that this is where we're going to eventually put that nuclear waste. It's a mountain in Nevada. It's got a series of deep tunnels that go under the earth, and it could store about 77,000 tons of nuclear waste. However, as you might imagine, if you lived in Nevada, or if similar was being proposed in your backyard, you might be kind of opposed to being the nation's dumping ground for all of their radioactive waste. So there is a lot of movements to not put all of the radioactive waste in this location. And there's also other questions. For example, Nevada has the fourth highest number of earthquakes in the nation. So is that a concern? If we store all of the nuclear waste underground and then there's a lot of earthquakes, could it get into drinking water? Could that cause a series of issues with the containment? Government geologists have said that it will actually probably be okay given its location and the way the Earth is kind of formed at that location. They probably shouldn't have to worry about the earthquakes at all. So currently, this storage facility doesn't have any nuclear waste stored inside of it. Pretty much all of the nation's nuclear waste is sitting in dry cask storage on site at the nuclear power plants, and it's just building and building and building. And we know we have to put it somewhere, but and this is not the only location. There are other locations that there have been projects funded to explore and develop and to try to come up with places to put it. Funding for various projects has been cut and reinstated through various political administrations. And it's been in political limbo for so long that if we were to start opening up Yucca Mountain for business today, right, we just start sending all of the nation's nuclear waste there, it would be full. And we would have extra nuclear waste. We already would need a second facility of the same type in order to actually meet our needs for storing this waste. So the problem's only going to get worse. Eventually, we are going to have to decide a place to put all this stuff for the thousands and thousands of years it'll take for it to become safe to interact with.